போயிடுச்சுமா.
ஓகே சார். எனக்கு ஃபர்ஸ்ட் பேஜ்ல இருந்தே இதாகல சார்.
அது நீங்க இதுல லைவ் போறதுக்கு முன்னாடி
ஆ.
வேற ஒரு பேஜ்ல யூடியூப்குள்ள இதுல லாகின் பண்ணி வச்சுக்கோங்க.
ஓ ஓகே சார்.
ஸ்டுடியோக்குள்ள.
ஆ. இது வேற மெயிலும் ஓபன் ஆயிருந்தனால அதுதான் இருக்கு போல. எனக்கு இன்னைக்கு இதுல இருந்தே முதல்ல இருந்தே ஸ்டார்ட் மீட்டிங் கொடுத்தேன்ல சார். அது வந்து அந்த பேஜ் எனக்கு எதுவுமே லோட் ஆகல. நிறைய அதனாலதான் இதுவும் எனக்கு ஏன்னா யூசுவலா நான் இங்க லோட் பண்ணிருந்தாலும் அங்க சைன் இன் பண்ணா கூட எனக்கு லாகின் ஐடி கோ லைவ் கொடுத்துருவேன். இப்போ இந்த பேஜ் எனக்கு எப்படி ஹாஃப் லோடிங்ல தான் இருந்தது. அதனாலதான் அங்க லோட் இப்போ உள்ள போயிட்டேன் சார். அங்க சேனலுக்குள்ள தான் இருக்கேன்.
சேனலுக்குள்ள இருக்கீங்களா? இப்போ லைவ் போயிட்டு இருக்கு.
ஓகே ஓகே சார்.
ஓகேவா? சோ நான் உங்களை திருப்பி ஹோஸ்ட் மாத்தி விட்டுறவா?
எஸ் சார் எஸ் சார். தேங்க்யூ சார்.
ஓகே. ஓபன் ஆயிடுச்சா பேஜ்?
எஸ் சார்.
அதுல நீங்க முடிச்ச பிறகு அந்த யூடியூப் ஸ்டுடியோல எண்ட் ஸ்ட்ரீம் கொடுக்கணுமா? அது நிறைய தடவை கொடுக்க மாட்டோம்.
ஓகே சார்.
அங்க இல்லைனாக்கா அது லைவ்லயே தான் காமிக்கும். அவ்வளவு டியூரேஷனுக்கும் அது ரெக்கார்டிங் ஆகிட்டே இருக்கும் யூடியூப்ல.
ஓகே ஓகே சார்.
நம்ம இங்க ஸ்டாப் ஸ்ட்ரீமிங் கொடுத்த பிறகும் அங்க யூடியூப்
கண்ட்ரோல்ல போய் கொடுக்கணும்ல?
யூடியூப் ஸ்டுடியோக்குள்ள போயிட்டு ஸ்டாப் எண்ட் லைவ் ஸ்ட்ரீமிங் கொடுக்கணும். இல்லைன்னா அங்க ரெக்கார்டிங் போயிட்டே இருக்கும் யூடியூப்ல.
ஓகே ஓகே சார். சரிங்க.
அது மாதிரி அங்க எண்ட் ஸ்ட்ரீம் கொடுத்துட்டு அதுக்கப்புறம் நீங்க அந்த லிங்க் போட்டதையும் டெலீட் பண்ணிடுங்க.
அது ரிமூவ் ஆப்ஷன் இருக்குல்ல சார்? அது
ஆமா. அது மாதிரி அன்னெசரி கமெண்ட்ஸ் ஏதாவது வந்துச்சுனாலும் அந்த கமெண்ட்டை டெலீட் பண்ணலாம் நீங்க.
ஓகே சார்.
ஓகேவா?
தேங்க் யூ.
ஓகேம்மா.
Thank you, sir.
சரிம்மா. நான் லீவ் பண்ணவா மீட்டிங்க?
எஸ் சார் எஸ்.
ஓகேம்மா.
Nancy ma'am, is it still going on live?
Wait Chitra ma'am, I'll stop this. Let it be. ஆமாப்பா யூடியூப் லைவ்ல தான் போயிட்டு இருக்கு.
சரி ஓகே.
Chitra ma'am.
Yes ma'am.
Can we admit the participants ma'am? It's almost time. Everything is okay? whether any PPT sharing is there by Gokul. Chitra ma'am.
Hello.
Ma'am.
ஐயோ நான் என்னடா மியூட்லயா இருந்தேன் கடவுளே. Okay ma'am, everything has been checked already, the presentation of the speaker also. We can just ask the speaker to switch on his video and then start admitting the participants.
Yes. Do it.
Mr. Gokul, are you there? Yeah, thank you. We shall start admitting the participants now, and we'll start the session at sharp 5, Mr. Gokul. Is that fine?
Yeah. Fine.
Is everything fine from your side? Shall we admit the participants?
Yeah, definitely. Yeah.
Yes, thank you.
No problem. Yeah.
Nancy ma'am, we can admit the participants.
Okay ma'am.
Nancy ma'am, shall we start?
Yes, Chitra ma'am, ready to go.
Yes, ma'am. Let's start with our today's session. A very happy evening to one and all present here. Success usually comes to those who are too busy to be looking for it. With this quote in this warm evening, to refresh and create an impact onto the minds, Department of Electronics and Communication Engineering, Savita Engineering College, brings to you a webinar as a part of the SEC Alumni Series, Impressions on Circuit Obfuscation and Analog Mixed Signal Design Approach by Mr. Gokul Ravi, MS in Electrical Engineering, State University of New York, University of Buffalo. A glimpse of our college and department. Savita Engineering College, established in the year 2001, an autonomous institution which follows the Finland-based education model, and we march towards less is more concept. Our college makes the students job ready by providing Industry 4.0 ready curriculum which imparts the 21st century skills. Project-based learning integrated with subjects improves the student skill set and makes our learners to be the best, which is the motto of our college. The Department of EC was established in the year 2001. Our vision is to develop the department into a state-of-art with center of excellence in electronics and communication engineering education on par with global standards. The Department of EC has well-experienced faculty of proven ability and diverse specialization. The faculty actively involve themselves in research in the fields of robotics, VLSI, MEMS, image processing, and embedded systems. I would now like to introduce the guest of our day. Mr. Gokul Ravi started his master's degree in 2019 at the University of Buffalo, majoring in electrical engineering. His focus of study area is analog mixed signal devices and crypto systems. Presently, he has started his graduate research as fellow student under Dr. Arindam Sanyal under analog circuit IP protection. Mr. Gokul Ravi has worked on projects from cross-domain and tried to encapsulate the ideas to obtain a focused research. Some of the academic and working projects carried out by him include design of MIMO communication link and smart antenna, and AMS circuit filter and their application in image crypto system circuit design with deep learning neurons. He has also published a literature review paper on IoT security, which includes advanced machine learning algorithms for training and reducing the risk of exposure of the system-sensitive data. We are very happy to have you with us today, sir. You may please take over the session now.
Yeah, thank you. Hello everyone. So today's topic would be circuit obfuscation and analog mixed signal design approach. This basically comes under the field of cryptography and CAD designs and application in AMS. So firstly, we need to check on what is circuit obfuscation. So it's a process by which we can conceal the properties of an IC that been produced by a company. So generally we we conceal the IP properties like SCRDS, that's a serial and destination points, some of the PLLs and DACs and ADCs used in there. And we mostly concentrate on the physical layer of the ICs. So why do we need circuit obfuscation? So this is generally, we need to stop the IP privacy, and we need to stop hardware trojans entering into the ICs, which may cause data leakage, uh, which in turn may have an great impact on the data that companies or personal computers are being used there. So and another main disadvantage of having these IP piracy would be IC overproduction. So suppose like if an company has an netlist of an IC, then they can produce the ICs that replicate the ICs from the companies that generally have the patent for them. So this would be the major problems in circuit IP. So why do we need a network circuit? I mean, circuit obfuscation. So see, as globalization and de-verticalization of semiconductor supply chain has resulted in IC design. So many companies they wanted to go fabless, which means that they do not need to produce their own chips. So they give their chips to and render or in third party IC production. So like Apple, they doesn't do not produce their ICs in US. They generally outsource it to China. So the factories work on their ICs and return back the ICs to US so they can assemble it here. So yeah, the main problem here would be that if the netlist or the layout of the chip that the manufacturer is producing may get leaked at some time, or the company may find a malicious act. So malicious act like they want to replicate the design of theirs. So then that would be a problem. So that's where circuit, we need to conceal the IP properties of an circuit. So these what would be the major impact of this circuit IP revelation would be like both financially and national security may come into an chaos. So like if there are some of the secret files that are kept in a computer, so and if the ICs that are being manufactured are implanted there, those data can be easily acquired through side channel effects there. So that would be a major drawback of circuit obfuscation. So yeah, is this only technique? I mean, what are the main techniques that we really follow to stop the IC being manufactured by an other person? So we generally use like logic locking, where the digital part of the ICs are being cryptographed, I mean encrypted, and only the perfect keys can open the analog IC or an DSP processor or any sort of ICs that the company manufactures. So that would be one of the design for trust techniques, and the other would be IC metric and watermarking. Some of the companies, they actually watermark their chips and also their layouts that they really want to send from one place to other place. And IC camouflaging and split manufacturing would be another technique. So in split manufacturing, generally that company A, that's the origin company, that will provide the net list and what are the main key components and the main layout of the circuit that they really wanted to manufacture. So then the company A sends it to a company B, where company B tries to manufacture only the physical layer or the main base layer there, and they don't have any idea what would be the upper layer. I mean, the upper layer of an physical there. I mean, physical layer above the physical layer. So that would be one advantage there. And the third company would manufacture the second layer and the third layer, and finally a company 4 or a company D would generally synthesize an cryptographic system there, so that they can implement an encryption tool only when proper keys and proper input is being supplied to the IC or in circuit, then only the IC or the circuit would generally work. So we'll only we'll only look into logic locking in the present lecture here. Okay, as mentioned before, this is only a design approach for analog and mixed signal design. So where both analog and digital both play a part there. So both have their own properties and own layouts in their space there. So firstly, we'll discuss about how digital circuits can be really concealed in a way. So topics that would be covered under the digital section would be logic locking as we spoke before, and the other thing would be SAT attack. So SAT attack would be an attack that, an algorithm that can crack the keys of an digital hardware when we have a netlist of that, or we have an layout for that. So then we'll look into SAR lock. So what would the SAR lock would be means it's generally an tool that overcomes, that protects the circuit from SAT attack. So we'll see that whether SAR lock would be really enough to produce, enough to stop the IP piracy in an analog chips or digital chips that we manufacture. So starting with logic locking. So as told before, this is a set of techniques that really hinders the IP privacy. Hinders the IP privacy and overbuilding, and it really stops the reverse engineering attacks where we have a simple, where we have an main circuit that need to be protected. So the circuit to be protected would be revealed to the manufacturer or the person who really want to perform, replicate and chip that's being patented by other company. So generally it won't be protected, and some of the characteristics there can be traced back by using reverse engineering. So some of the comparators or XOR gates are mainly used in digital circuits as we go forward. So these can be traced back based on the algorithms and other encryption techniques here. So what does logic locking generally does? It adds an additional logic into a circuit by locking the original design with a security key. So which means that if you have an circuit that consists of like 3 AND gates and 2 XOR gates, then we include 2 more XOR gates or NOT gates in some pattern that the key cannot be, the output of the chip that we have manufactured doesn't properly work for a person who doesn't know the key. So let's consider an example here of gates that are being here. So ABC would be the inputs to the gates here, and we consider an output Y. So let us consider this complete thing is in an chip, and company generally wanted this to be manufactured, and they send it to a third party for third party foundry to manufacture these chips. If this chip gets this chip layout gets out, then people can generally manufacture it and replicate it. So how can we really avoid it? So company generally sends this layout to one of the foundries that they do, and they generally manufacture the first layer, and in the second layer, these second layer and second manufacturer, generally what he does is he adds and gates in between of those things. Like we can see the red colored gates here. So they generally have an keys as an input to them. So K1, K2, and K3 would be the keys. Only when the proper key has been entered here in K1, K2, and K3, then only the output that we expect would come, or else this circuit may have some alternate output that we do not want here. So so let's consider that the current key value here is 110. Then the output of the equation y would be related to the a, b, c in such a way that it's the correct output that we really require here. So that would be one example. And this would be an example where we can have an inverters of those in such a way that everything is same, but we add an inverter at the end of the thing. So then sometimes key values may be the same for some of the inverting and non-inverting, depending on the logic circuit that we really design here. So we generally avoid the situation where we have an same amount of same keys for different logics. So when we have same keys for different logic, then it can be easily cracked. So we need to have a unique layout in such a way that it is being booleanly satisfiable through all the conditions that we really consider in a space of NP. So yeah, the thing SAT attack. So as mentioned, SAT attack is generally an NP complete problem. So what does NP means? It has NP turns of cycles that can be repeated, and it can break an code or an digital logic within seconds, depending on how properly we encrypt the circuit. So the main key, generally SAT attacks would be used on the previously shown layout. So the encryption is being broken there, and we have a proper layout, and the third-party foundry can easily manufacture or replicate it. So we really need to avoid that. So firstly, to see how these SAT attack can be stopped, we need to know how SAT attack works and what are the key parts there. So generally we consider a threat model of attack. So we generally name the netlist or the ICs that we get as an oracle. So so the main thing here should be that the oracle that we design needs to be something that is resistant to SAT attack. So starting that, some foundries may have the locked netlist with key gates. So which means that they may have the circuit with encryption embedded in it, but people cannot see, people cannot know what would be the key there. So they try to crack the code there. So another thing would be that there's a function IC with correct key embedded inside. So like we may have an ADC for example, we do have an ADC chip manufactured by consider like a Texas Instrument. So if and only if a proper key is being supplied or a proper input level is supplied to the circuit, only then the IC may function. So here, the person who is trying to replicate the IC has both the functional IC, the main IC component that we need here, that the person tries to manufacture, and he does have the correct key. Then the attacker can easily sort what are the inputs to the IC, and he can observe the outputs easily by cross-checking it with the correct key that he has. So these would be the main access to the foundries that try to replicate or piracy the chips that are being manufactured. So yeah, let's start how SAT attack generally works. So consider a flow chart. I mean, we can explain it through a flow chart. So we do have an netlist that's been locked. For example, here we are considering only the netlist that's been locked, and we don't have an key to access what are the outputs in it. So firstly, what we do is we cannot run these netlists or RTL files that we get from the foundries, I mean, from the manufacturer, wouldn't have any like form that can be fed into a computer or into a code like Python or C++ or any sort of programming language. So these netlists need to be converted. So we generally use an CNF form, which is generally like a Boolean equation with its own replication there. So it has a different sort of replication that's very similar to the Boolean expressions that we use in digital circuits. So firstly, we need to convert the netlist, locked netlist to an CNF form. So then we do have a SAT solver that's been installed in a computer or any sort of hardware devices that we use for breaking the keys for the locked netlist. So we start feeding the SAT solver with the locked netlist that's being in a CNF form. So generally in CNF form we have a input in form of clause. So like we have an input X, output Y, and then key K. So it would be in generally as a clause like here it would be an X, and other would be Y, and other would be K. So we have we have these clause of each input or the digital design we have we have all the iterations and all the clause that we really require from the netlist. So we start feeding those to the SAT solver here. Then we generally find if there is a dip that exists. So firstly, we need to speak about dip before we start the process. So dip would be an different independent code that we really need to search in a key space. So like we have a key space sample space like omega. So we need to search the keys that have been scattered into the sample space. So the keys may be like an 32-bit, 64-bit, 128-bit. It really depends on how far we need to develop a key or encrypt a key there to provide the safety from IC being pirated. So we generally search for every key space that's in the sample space here. So we generally have like consider if it's an 5-bit input, so we have 3 zeros and 0 1. So it goes on. It starts on searching each and every. Oops, sorry. Yeah, sorry about that. So we need to feed those CNF to the SAT solver. Then we find if there exists a dip. So if there is a dip, then it's a satisfiable condition. Then these dips are being fed into the functional IC that the person or the third party person who really needs to manufacture a copy of that chip. So then he tries to he tries to put those keys to the functional IC, and he checks whether the input is correct or not. He tries to check with the input and output pair. He generally checks if the output that he required is being seen in whatever display that he uses. So if the key is wrong, then he might not cannot see the proper output of at the end of the IC. So what he tries is he then tries to loop every iteration. So the first key would be slashed out, and it goes for the second dip. So it goes for the second dip, and so on. It continues and continues and continues. It generally sats the thing until the functional IC produces an output that's been really expected by the person who tries to copy the chip. So what happens next is then if there a dip exists, then it unsats the condition. Then the SAT solver says that's an correct key, and the process gets stopped. Unless and until this process unless and until the person who tries to manufacture the chip finds an output that he requires, he generally loops on those to the SAT solver. So when in a case where a dip doesn't exist, then the Boolean expression gets unsatisfied, and then the correct key, that would be the correct key that what he is been expecting there. So he stops the process. So this would be the SAT attack algorithm that generally persons who try to copy the chip uses to find whether the find the keys that that's been encrypted by the company. So here would be an example for an SAT solver. So this was run on my friend's computer. So yeah, you can just see that we are trying to load the SAT solver here, and we are trying to see. We are trying to load the samples here. So yeah. So we generally have different CNF form for different circuits. We try to run the SAT solver on those, and we get that the CNF is not satisfiable and the key can be broken here. And the assignment results in the following fully assigned CNF, and we get the clause that we really required there. So yeah, after speaking about what SAT attack is, so we find it a problematic thing that really checks on our content or IC content that we really, that we use in our daily life. So yeah, first persons to start these things were, they started to find a solution for how to stop this SAT attack. So they first started with SAR Lock. SAR Lock was the first resilient solution for the SAT attack. So generally SAR expands to SAT attack resilient logic locking. So generally we here have an a logic cone that you can see here, which is the main circuit that need to be encrypted here. So we do have an comparator and a mask circuit here. So generally what comparator does is it compares the input that we give to the logic cone and the keys that we in person give to the circuit to check, to activate the circuit. So what happens here is if the comparator output is not correct, or it's a 0, then there is a flip occurs equals to 1. Flip equal to 1 occurs. Then the output of the circuit here wouldn't be as expected unless and until both the input and the keys are same, or that satisfies the comparator condition here. As it's stated as question mark. So it may be different. It may be any type of comparator there. So it really depends on the person who tries to implement a comparator circuit there. So yeah, then these outputs are being masked, and so these are flipped, and then it really checks with the final gates, like final XOR gate, and it generally produce an output Y, which may be a correct output. So yeah, for a K bit, the additional logic would consist of K plus 1 2 input XOR gates here, and 2K plus 1 AND gates that we require in the comparator circuit here. Generally, on increasing the key size, the overhead area grows linearly. So as we try to implement more number of keys, we need more number of input to be taken by an IC or gates that are being implemented in an IC. So as the key size gets growing on, then there would be an overhead grow, which means that generally the IC may start growing there linearly, which exponentially increases the dips. So when we have more number of dips, it becomes difficult for the person to crack the code here. So it takes more time than expected in the before key. So like if we take and 32-bit key input, then the SAT solver may solve the circuit in 10 seconds or 50 seconds. But when we try to increase it to 64-bit, then there is an exponential increase of dips, so which in turn increases the time that needed to be cracked down. So the time gets increased on. So generally we now use 256, 512, and 1024 bits of keys. So generally those ICs would be, those ICs would be small, but the construction of the transistors and the gates in those circuits would be really heavy and hard. So that would be the sword lock for now. So yeah, is Sorlock good enough to stop the SAT attack? Generally, when Sorlock was first implemented, they found that it was one of the best solution, as it was the first solution. So people try to interpret those logic cones or the encryptor circuit that's here. So they try to reverse engineer this process, and they were able to crack the blue part here. So this logic cone that we implement here is generally the original circuit. So when a person tries to reverse engineer the circuit here, encryptor circuit here, he can remove the comparator and the masking part with the gate here, and he can generally get an access to the original circuit, that's the logic cone as mentioned here. So yeah, it can be easily identified. The comparator and mask can be easily identified, and reverse engineering can be applied here to break the circuit. So yeah, then we do have a threat for the original form that's been implemented as a logic cone to be rebuilt and been cracked. So yeah, then Sorlog doesn't support the way it needs to be supported. So it need to encrypt a circuit, but when we reverse engineer, we can decrypt the circuit easily, and we can have an access to the logic cone that we have. So then okay, after Sorlog, other people started to research on different locking systems, and the other locking system was a TTL Lock. Generally, what happens here is we don't have a mask circuit here, and we don't have a mask circuit, but we do have a comparator here. But the masking circuit and an initial part of the original logic cone or the original circuit is been modified in such a way that the mask part that was in Sorlock is been removed here and added to the modified logic cone. So what happens here is the original circuit is being masked, and the revealing of those identities would be really difficult here. So yeah, this was an successor for Sorlock after some days. Then yeah, does this have a problem? Yeah, it can be broken. It can be break using Sorlock or other mixed locks that those algorithms that was implemented after SAT attack. So like double dip attack can easily break TTL lock, and where they can easily have an access to the original cone that they were looking for. So yeah, generally what happens here is only one key, like here for K0, I mean K0 key, that is the correct key here, and here the key can be activated from K0. So what happens here in TTL lock is it tries to generate an one input pattern. So what happens here is at least one of the bits in and key may be deferred by the by the encryption technique here. So that would be the one input pattern that we see here in the red shaded boxes. So the key K0 would be the actual key that really unlocks the circuit here. So after the intro of mixed lock circuits and mixed lock circuit, other algorithms that can break the circuits that we have, researchers try to develop an two-layer logic locking. Here generally we do have an SOR lock and SLL. So SLL would be only the upper part of the TTL lock, and the SOR lock would be similar. But it does have a scrambler which generally mixes the input or the keys that we feed to it. So what happens here in these two-layer locking is, firstly, the input in and K1 key is being supplied to the logic cone, and K2 and K1 are being supplied to the scrambler here. So what happens here is both K1 and K2 are being scrambled in a way that it takes time for the perfect identification of the key there. So then this scrambler generally is sent to an comparator where it compares both the keys K1 and K2. Here the K1 and K2 generally may be an K1 XOR K2 or K1 multiplied by K2. It really depends on what sort of scrambler circuit that we really use here. So then the comparator generally compares the logic between the input and the original key K, which is a combination of K1 and K2, and then it tries to see the output Y. So yeah, this was another logic locking method that was implemented after TTL lock. And we do have, generally the scrambler scrambles all the keys that we give to the SOR lock here. And these K1 and K2 are, keys are designed or made in such a way that they do have a dependency. So like K1 really depends on K2 here. So if K2 changes, if either of the keys are wrong or both the keys are wrong, then we don't have an proper output that we really expect. So both K1 and K2 are dependent, closely dependent here. So yeah, it makes it makes a sample space where both the keys are dependent, which means that it takes more time to generally crack the keys when they are dependent. If the keys K1 and K2 are independent, then it would be an easy trick to really check out what the keys K1 and K2 are. So here we do have a table that really that was taken from a research paper from SORLock plus two-layer logic locking. Here we see that we do have an RLL, which is generally a random logic locking where random numbers are generated from a circuit and are fed. Random numbers are generated, which acts as a key for the circuit. But yeah, random logic locking do have a problem there, because after a certain intervals, all the keys will repeat in a loop. So yeah, that was a problem in RLL. So they tried to move to an SLL logic, which had a decent number of dips. So when people try to move to SORLock and SLL, there was a huge, literally a huge exponential increase in the dips that we have. So you can see that dips are 19. So it took a time of 0.4 seconds to break the circuit. And for an SSL, there was an dips of 26. It took 0.7 seconds to break. But when you consider an two-layer logic logging, logic logging, so here we do have an dip size of 4.3 into 10 power 9 dips. So that's really a huge number, and it takes approximately 3.1 into 10 power 9 seconds to break that. I mean, that's a huge time for that's a huge interval for breaking and space here. So when we consider the area and power and delay, we do have a decent decent property that really, I mean, decent numbers that really have much, I mean, more close to the SLL part. So yeah, Sarlock and SLL would provide a better guarding technique for a digital circuit here. So we do have different sort of attacks here. So we do have an sensation attack where we do have an access to both the locked netlist and activated IC. So here the bits are being randomly checked for the proper output. I mean, randomly checked for the keys. Then we do have a logic cone analysis where we do have the locked netlist and activated IC. But here the problem would be that brute forces can easily break the logic cone analysis here. So then we did study about came across the SAT attacks and SAT based algorithms that rules out incorrect keys related. So yeah, those dips and incorrect keys generally get overruled there, and we do have, I mean, we can generally break the circuit here. That would be one of the attack, and there's another attack by name of hill climbing. Yeah, here we do have the locked netlist and the test patterns that are being generated by the analog IC or the IC that we really need to encrypt. So what happens here is based on the test patterns and responses from the IC for different key inputs or keys that we give, we can generally collect those data for each key, and we can feed it to an machine learning algorithm, and we can generally crack the code within seconds. So yeah, here the Hamming distance between the keys that we really use, I mean, that we use are Hamming distance are being found between the two responses or the responses that we get, and we do have an attack by name of side channel attacks where temperature generally plays a key. I mean, temperature from the thing and timing analysis generally breaks the circuit. So using these temperature data and the data from the timing that it takes to check for the keys that we give, we can break a circuit there too. So yeah, I mean, here we at present are working on an circuit logic. I mean, logic blocking that really overcomes the SAT, I mean, newborn SAT attacks that are being implemented nowadays. So we are trying to implement a logic locking presently in our lab. So yeah, hope so we get a proper output there. So yeah, next thing we would discuss about the analog circuit obfuscation. So we sort of completed of the first half where we talk about the digital part of locking. We also need to lock our analog circuit, or we can only lock the analog part of an circuit that we really require. So here we will talk about the parameter bias technique in the analog locking, where we'll see how the biasing parameters really plays a key role. How to really how to really hinder the IP properties of an analog circuit. Then we'll talk about analog SAT attacks, where we generally see a SAT attack that's more identical to and digital side attack, but it differ in some terms. We'll check it out. So yeah, I mean, when we come to protection of an analog circuit, we do have some significant differences between designing and digital design and an analog IC, completely analog IC design. So we need to have a more precision and biased condition in perfect biased condition in an analog devices. We do need to have an great it does have an greater sensitivity to noise and temperature. So the place we manufacture, the place we test these circuits need to be in a proper thing, or it may affect the analog IC design that we design here. So signal integrity plays a major role here too. So yeah, it does have a greater part in analog IC design. We need to have an what do you say, a closer noise margin. So we don't have more amount of noises in our design circuits, that I mean in our analog IC designs. So simultaneously we generally also need to consider all other design parameters, like we need to check on the phase delays. We need to check on the timing analysis of the circuit. We need to check on the number of fan in and fan outs conditions there. So we start with voltage bias, biasing node here. So we do have an PMOS and NMOS connected back to back here. So generally under an voltage applied, it generally acts as an resistor. So we consider those PMOS and NMOS as an resistors R1 and R2. These are directly, I mean, these are actually these resistance R1 and R2 are proportional to the width of the transistors that we use here. So generally we do have an W by L ratio while designing the ICs here. So it really impacts on how much gain we really expect from the output, I mean from the circuit here. So so we can see this would be an unsecured system. You can say it as an unsecured voltage bias circuit, and we do have an circuit that has an what do you say, an encryption here. So we are trying to decrypt the keys here. So we give a certain potential, or we apply a certain voltage to the inputs here, and we compare it with the keys, and we only try to activate the MOSFETs, or I mean the MOSFETs or PMOS or NMOS that we really require. So if consider like we do have an like 15 to 20 transistor here depending on the key size that we use, only under a certain condition of a key we can activate one of the one of the PMOS and NMOSs, and that would be the perfect only when perfect key 1 and key 2 are applied, we do get an output of an required gain that we really expect for. So if there is an polarity change in the input that we give, yeah, that too would affect the circuit here. So all these considerations, all these parameters, we need to consider those. If there is a timing lag here in the decryptor circuit, then we do have a problem activating the improper PMOS and NMOS, which may lead to the gain of the circuit to be improper. So yeah, you can see an decryptor block that's been enlarged here. So we do have a gates there. We don't implement any digital circuits here. So we try to implement with PMOS or NMOS here. So generally the key tabs are tabbed here. So according to the input or the key we give and combined with the voltage that we apply, generally the PMOSs or the NMOSs are activated, and we generally get an output. So yeah, that was the thing needed to be showed for the decryptor enclosure circuit. So as we spoke about current biasing, we also need, I mean, we spoke about voltage biasing. So we also need to see if there is a way that current can be biased at a node, and can we get an can we really use that for securing the analog IC that we use? Yeah, definitely, definitely we do have an MOSFET here. So we do have a transistor here. We try to find the current that ID, I mean, drain to source current that that flows through the transistor. So we do have an equation for the current to drain equation, I mean, drain to source equation here. So here we can see that the IDS is directly proportional to W, the width of the IC that I mean, IC, I mean, the width of the transistor that we use. Depending on the keys that we give here, the current is being, I mean, the current is being generated, I mean, current is being flowing through the circuits there. So depending on that, we do have a circuit block at bottom, which gets activated by the source we give from the keys. So the proposed technique, this current biasing node would be more of an width dependent circuit parameter, where including capacitance and gain. So yeah, that would really try to affect, I mean, the capacitance in, I mean, we may have some shunt capacitance that be, I mean, shunt capacitance that being generated around the thing here. So when we try to design and switch or and MOSFET, we really need to bias and I mean, we need to properly bias the circuit. We need to have a proper design knowledge and how to avoid these capacitance that really abstract the process of the decryption, I mean, the encryption block here. Yeah, here I mean, we sort of took these results from an research paper where the authors tried to implement this one, I mean, these analog ASAT in two-stage amplifier. So there's an connection of two stages amplifier that's being cascaded here. So here we really expect a gain that's been marked by the blue dotted lines here. So depending on the width of the transistor that we use, the gain may differ here. So only for an say like 1 micrometer or 1 micrometer, 1 micrometer of width, the gain is like 70 dB. That's the superior gain for, I mean, 70 dB. That's the gain what we really expect from a two-stage amplifier. So yeah, here only only a width between 0 to 5 micrometers. There is an we can see peak here that really meets with the gain point. So that would be the perfect key for the input here. So that would be the perfect selection size of the transistor width here. So we sort of try to deviate the experiment with a 40% of deviation here. So which generally in turn had an inverting result here. So at some point between 20 to 0 to 5 micrometer, we get a gain value that we actually require. So only depending on the keys that we give, the width of the transistors are being selected, and depending on those transistors, we get an proper gain that we really expect from an analog IC. So that would be about analog part of circuit obfuscation. So we start about analog mixed signal circuit obfuscation. So yeah, so what we try here is to combine both the analog and the digital part in such a way that we generally secure the circuit. So AMS circuits maybe like DAC circuits that we use, PLLs, VCOs, super heterodyne receivers. So these so not super heterodyne receiver, that would be an analog circuit. We generally use these ADCs and DACs in much of the audio application. So where we need an IC that's both that has both analog and digital components here, and that need to be concealed in such a way that its identity doesn't get revealed by an who tries to steal the identity there. So yeah, regarding we saw that DACs, digital circuits do have different logic lockings like SAR lock, SAR lock and SAR lock plus SSL, TTL lock, something like that. And analog circuits do have an analog analog SAR that really stops. That really stops from being. The IC being pirated. So for mixed signal design, we sort of try to implement logic locking here. So the mixed lock paper on secured mixed signal circuit via logic locking was a new technique where we do have a mixed lock. That was one of the best outcomes that mixed signal circuits can really have. For mixed signal circuits. So yeah, it's generally the same. It's generally the same as digital circuits. We do have an security key or a secret key here that needs to be that is used to unlock the correct functionality of the circuit. So we do have a common key, name it as KC. So yeah, let's start with mixed lock. So we do have an analog section here. We do have an locked digital section. We at present in mixed lock, we only lock the digital part of the IC, and we do not lock the analog section. We only lock the digital section, which supports as an input to an analog section using DACs in the middle. So we do have a tamper-proof memory where we can load our common key or the original key that helps in unlocking the circuit. We generally use tamper-proof memory here because we need to verify the inputs and the common key. So yeah, tamper-proof memory provides a space there for loading of common key, which avoids tampering of the common key that we use. So that would be the circuit for mixed lock. But we do have an an upgraded version of mixed lock here, where we do have a chip identification, which generally has an inbuilt key already embedded in the IC that we consider. So this would be a complete IC which does have an chip identification, where we already have hard coded the chip key here. So from the loader user, he generally loads the key to the memory. Then the XOR circuit here verifies the key using the chip identification key that we do have, and produces a common key there. So that acts as a key for the locked digital section there. So what happens here is this chip identification key cannot be revealed. This chip identification key will be only known to the the owner or the patent generator of an IC, or the person who tries to outsource his ICs for a large or mass production. So these only when the loader, when the user loads the key, he can check with the XOR circuit whether the not check here. It generally combines both the keys and prepares a common key that acts as an key part for unlocking the digital section of an mixed signal IC. So what are the properties that we generally take care in mixed signal would be like we do have many wide applications. As mentioned, we generally use the mixed signal ICs in data converters, PLLs, RF transceivers, many more. That has a wide application. So all these applications uses these mixed signal ICs, and these need to be protected. These need to be protected in a way that other foundries or other duplicate companies doesn't make a pirated version of the original ICs. So then these mixed lock technique is fully automatic, which means that we only load the circuit. We only load the key there, and the rest is left to the IC. Then it generally checks with the XOR gates there, and it generates a common key for the digital locked circuit here. Locked circuit in the IC. It do have a low overhead, which means that the area for both the digital section used for logic locking would be low when compared to the analog section. So when we try to implement analog obfuscation, so there we do have a more overhead, which means that it requires more space and energy for the circuit to start on. So for digital circuits, it would be really easy to load the circuits, and it does have a low area and low power consumption. So yeah, locking only the digital part would be an key part in mixed lock technique. So let's discuss some approach that we find for an AMS circuit. So we are trying to take a bandpass filter here, which Tau Thomas bandpass filter that's represented here. We do have op amps here. We do have an inverter with a gain. We do have capacitor. We do have resistors here. So here the resistors are generally tunable. So depending on the values that are being tuned for the resistors R1 to R4, the band pass circuit functions as per those. So like if we do require the band pass IC or band pass circuit to have an low pass and high pass of like 100 kilohertz of low pass and 200 kilohertz of high pass. So it depends. These frequencies are generally varied using the resistors. Yes. So when we do change the resistors, we do face some problems regarding the capacitors in the circuit. So we do need to take care of those two. The transfer function of the bandpass filter is given here. So which generally consists of the resistors and capacitors that we include here. So we generally here consider the R1 and R3 as R1 resistor, and R2 and R4 as R2 resistor. So as mentioned before, these resistors play a key part, a key role for deciding the center frequency and the quality factor of the circuit that we implement. These passive components that we use, like resistors and capacitors, really need to be designed in a perfect way, or need to be tuned in a perfect way, or we may not get the quality factor or the center frequency that we really expect. So here is a block diagram for a logic locked BPF circuit. So we do have a tamper-proof memory here to load the key from the loader, from the user. This key is generally fed to the digital part here, digital part of the section where the logic locked optimizer generally have an tunable, turning knobs, a tunable resistor gated there, which in turn supplies the resistors with an proper values. So we do use an ADC for feedback here for the logic locked optimizer. Depending on the perfect key we give to the digital part, the resistor values are generated using the resistor values are being tuned in a way that only the original key would provide the center frequency that we require. So so here we can see an normalized error graph for the outputs. So yeah, we do have two resistors here. Yeah, these may have some mean square errors for those resistors for an resistors. So we try to find an what do you say, a normalized error, so which can be used in finding the sensitivity of the logic locked circuit here. So which in turns makes the bandpass filter in a perfect way to operate. So we do have an comparison graph between execution and key size. So as we try to increase the key size, the more amount of digital part increases on the circuit, which doesn't concern unless and until we do have a larger key. So as we try to increase the key size, we do have an increase in the execution time that's been performed on the circuit shown before. So yeah, this would be the graph for the execution time to the key size we give. Yeah, here we can find an frequency versus, gain versus frequency wave here. So the blue part here represents the output of an bandpass filter with an low pass, low frequency and high frequency here, with an center frequency between 4.6 to 4.8. When we try to give an incorrect key at the input side, we do have a red dotted line that represents a flat line which doesn't have an what do you say, a central point or an low and high frequency bands to frequency bands that would be the response of an BPF, right? So we do not have that here. We do have a flat line. We do not have a frequency response that says where we do have the central frequency and what would be the quality factor of the circuit here. So the authors also tried to implement the same mixed lock in LNA. LNA stands for low noise amplifier. So yeah, low noise amplifiers are the trending circuits. You may say it as a trending circuits right now that finds many applications than any other analog, mixed analog circuits here. So we sort of, they sort of try to find the S parameters with the frequencies between the input port and the output port. So yeah, for the correct key, we do have an proper response. Proper peak, proper frequency response for the amplifier. For the keys that are incorrect, we do have an negative dip here that we can see with the dotted lines here. So that represents that the amplifier may have gone into oscillations, or the gain of the amplifier maybe too weak or improper there. So we do have another example for the bandpass delta sigma ADCs. So ADCs find much of the applications in audio equalizers and many of those. So we sort of we thought so we can have an example of on that too. So we do have an ADC input and ADC out here. We do have a modulator in between, which tries to convert analog to digital signals, and then we do have an oscillator circuit which generally mixes with the digital output there, and we supply these to the decimation filter, which in turn returns the analog analog signal that we require here. So we do have an LC bandpass modulator that authors designed. We do have a proper DAC circuits there. We really need to check on the inductor, on the capacitor, the passive components, which plays a key role for determining the cutoff frequencies for an bandpass filter. So yeah, improper design of DACs, or improper unlocking of DAC may provide the output to be somewhat distorted. We do have an output that we can check on. So yeah, we do have an output that of an ADC here. We do have an transient and frequency responses of the unlocked ADCs with proper key and improper key. For the proper key, we do have an red what do you say sine wave that we gave at the input. For an improper incorrect key, we do have distorted traces of distorted wave that traces in form of a sine signal. But yeah, that's some noise or some rubbish signals in the middle. So we do also have the frequency response where we can check the gain of the the ADCs there. So we check for the peak point, so we can confirm where the gain lies. You can see that for the correct key, we do have a proper frequency response tip here, so which defines where the gain is, and the circuit that's been unlocked with an incorrect key do have an distorted frequency response. So yeah, this would be an example for an AMS circuit. So when we start to discuss about AMS circuit design or circuit obfuscation, we really need to keep in mind about the design techniques that we use for digital or analog. We need to design whether we are locking the digital part or the analog part or both the parts. Whether any other unlocking techniques or unlocking codes like SAT attack may break the circuits here. So we need to carefully design the circuits in a way that IP piracy, IC camouflaging is being IC being manufactured at a different spot, or leakage of side channel effects. Leakage of side channel information from the devices we use, that really causes a problem both financially and we do have an national security threat there. So yeah, cryptography and plays a key part here. So in designing how these things work. Regarding the SAT attack is as we discussed, it's an NP problem. So it has it can crack things in with ease. So it can crack the things depending on the sample space there. It tries to eliminate all the dips, so which in turns generates proper keys. If we try, generally we are trying to use a single dip method in SAT attack. So when we try to remodify the SAT attack, we do get SFLL method, that where the attacks, I mean functional analysis, I mean fall attacks, where they sort of use a double dipping method, which exponentially reduces the time of finding the dips. If a single dip method takes 10 seconds, a double dip may take 2 seconds or 3 seconds. So it tries to eliminate the unwanted samples from the sample set very easily, and that can be a problem for the circuits that we design. So at present, we are working on double dip. I mean, the thing that, I mean, we are working on the logic circuit that's not been cracked that would really resist the double dip and the fall attacks that are been recently performed in 2019 IEEE symposium. So yeah, we are trying to sort of restrict those here. So yeah, that would be the references paper. Okay, that would be the end of the presentations. If you people have any questions, you can, yeah, please.
Yes, sir. Thank you very much. That was a wonderful session, and we convey heartfelt thanks to you for sharing your valuable knowledge with us. So we've actually got a few questions from our participants.
Yeah, definitely.
Yeah, the first one is, can I know what is a logic cone?
Okay, logic cone is the original circuit that we try to what do you say, camouflage there. So the original circuit is rephrased as a logical cone there to represent the triangle part. So it's generally an alternate name for original circuit that we use there. That's nothing more than that. It's the original circuit that we use.
Okay, thank you very much. The next question that we have, does the extra circuitry used in obfuscating a system reduce the efficiency of the system? If it is so, then how can it be managed?
Okay, when we come to the execution time there, I mean, it was regarding the execution time, right?
Like when we use extra circuit, it might reduce the efficiency. If it reduces the efficiency, how can that be managed? That was the question.
Okay, when we sort of move to analog part, then we do have an reduction in efficiency, but this I mean efficiency in sort of timing there, not the gain or the output that we expect from the IC to be designed. So it's generally regarding an timing circuit there. And mostly those, I mean, mostly the designs generally won't have any effect on the gain or the original characteristics of the IC that we are trying to protect there.
Yeah, great. And one last question that we have from a participant. If the gain of the circuit deviates by 40%, then in what way can we call it to be an effective circuit?
We are not sort of trying to deviate the gain there. We are only trying to deviate the frequency level. So we are trying to, what do you say, the percentage of W by L ratio that we consider there. We are trying to only to change those levels. So if in the first case, if we have an level, I mean, W by L value of 1 by 10. So we are trying to reduce it or increase it by 40%. So we are trying to check it for 40 by 140 or other simultaneous thing. We are trying to, what do you say, plus or minus the 0.1 value that we get for W by L, increasing it by 40% and reducing it by 40%. We are trying to simulate the output for different W by L values. The 40% change is only for the W by L values there, not the gain.
Okay, so thank you very much. So that's it we have for the question answer session today. And we thank you once again for taking up your time and presenting such a valuable, knowledgeable session for us and for all our participants gathered today. Thank you very much, sir.
Thank you. Thank you.
Yeah. And we thank all the participants for joining with us today. Hope you'd have enjoyed the session well and all the questions have been answered by our speaker. I would like to announce about our upcoming webinar. Our upcoming webinar is on Social Media Addiction, Hacker's Perspective by Mr. Ashok Kumar Mohan, Chief Forensic Consultant, cyberneon.in, Assam, scheduled on July 13th between 4 p.m. and 5 p.m. I request all the faculties and students to attend the webinars and get benefited. Meet you all in the next session of our webinar series. The feedback link has been posted in our Zoom chat box as well as the YouTube live streaming page. Kindly fill up the feedback form with correct email IDs. The participants will be receiving their e-certificates to the filled up email IDs within 2 days after the session gets over. I repeat once again, kindly fill up the feedback form with the correct email IDs. The participants will receive your e-certificates within 2 days after the session gets over. And kindly complete filling up the feedback form within 10 minutes after the session gets over. The feedback link will be closed 10 minutes from now. So kindly fill up the feedback form with your correct email ID. This feedback link will not be shared through WhatsApp or through email. So kindly use the link posted in the Zoom chat box and the YouTube live streaming page. Thank you all for your participation. Stay safe. The feedback link has been posted in the Zoom chat box and YouTube live streaming page. Participants kindly complete filling up the feedback form within 10 minutes after the session gets over. E-certificates will be mailed to your email IDs within 2 days after the session gets over. And I would like to announce about our upcoming webinar. Our upcoming webinar is on Social Media Addiction, Hacker's Perspective by Mr. Ashok Kumar Mohan, Chief Forensic Consultant, cyberneon.in, Assam, scheduled on July 13th between 4 p.m. and 5 p.m. The link for registration has also been posted in the chat box. Kindly make use of it to attend the next session of our webinar series. Thank you.